In this video, I'm going to start discussing chemical reactions. So recall that a chemical change is when substances react to form products that have different properties. This occurs with a chemical reaction. This always involves a chemical change. Remember that a chemical reaction is when atoms of reacting substances rearrange. So nothing is created or destroyed. There is conservation of mass. We're just taking the atoms from the reactants, rearranging them, and forming the products. The new substances with new combinations of atoms are formed, and these new substances have new properties. Things like boiling point and melting point and solubility and things like that. To show this, we use what's called a chemical equation. This tells us the reactants that are used and the products that are formed, and these can also include things like the change of heat. These are what chemical equations look like. We have the reactants here to the left of our arrow and the products here to the right of our arrow. So the reactants are the things we're putting into the reaction. The products are the things that are produced in the reaction. And when writing a chemical equation, the formulas of the reactants are always written to the left side of the arrow and the products to the right side. And some common symbols that you may have noticed in the previous examples. We can have a delta symbol, so that's the uppercase Greek letter delta, meaning that heat is used. We can have this S in parentheses, meaning a solid, an L in parentheses, meaning a liquid, a G in parentheses, meaning a gas, and this AQ in parentheses meaning aqueous, meaning that it is dissolved in water. So if we look at our examples here, we can have these AQs telling us that these are dissolved in water. We can have these L's telling us that these are liquid, G's telling us that these are gases, S's telling us that these are solids, and this delta here telling us that heat was used to drive this reaction. So these little symbols here are telling us what each of these substances are as far as their state of matter. And so these are important in a lot of these chemical reactions. Predicting these states of matter can be something that's kind of tricky. These are going to be a few rules of thumb here, so not hard and fast rules, but we'll talk about a few things that you will want to use when trying to predict these states of matter. Ionic compounds will either be solid or aqueous, and we would need solubility rules to determine which, and we will cover the solubility rules in later videos. The take-home message here is that if you have an ionic compound, it will either be a solid or it will be aqueous. The diatomic molecules of hydrogen, nitrogen, oxygen, fluorine, and chlorine are always gases, where bromine is usually a liquid and iodine is usually a solid. The elemental form of all metals and any other nonmetals that I haven't discussed here above are almost always solids, unless it specifically says in some kind of problem that maybe we're doing something in the liquid or gas phase. They're pretty much always solids, with the exception of mercury and gallium, which are liquids at room temperature. The other gases that often occur, so these are gases you often see in chemical reactions: carbon dioxide, carbon monoxide, methane, ammonia, NO, NO2, SO2, and SO3. So again, these show up quite often in our chemical reactions, and these are pretty much always gases. Water will usually show up as either a liquid or a gas. You kind of have to use the context of the reaction to determine what it is. For instance, if we're doing a reaction in an aqueous medium, the water will usually be a liquid. If you see water in something like a combustion reaction, it's usually going to be a gas. If you are unsure, then gas is often a good guess. So a lot of chemical reactions that you run across in textbooks are done in the gas phase. And so unless any of these other things don't apply, you can oftentimes just assume a gas, and that would probably be a good guess. But really the only way to actually be sure of the state of matter is to know at what temperature a reaction is occurring and know what the melting and boiling points of the reactants and products are. Or if we're looking at ionic compounds, to know the solubility rules for ionic compounds. So when we're writing our chemical equations, one thing to remember is that these 7 diatomic elements are always written as diatomic molecules. So if we have hydrogen in a reaction, we would not just write that as H, it would always be H2. So when these are in their elemental form, you always want to use the diatomic form of it. So for instance, with reactions like this, we would want to use our diatomic forms of these elements. And you always want to use that subscript, because having the subscript is not the same as having a number in front. And that's because the subscripts indicate that the atoms are bound together, where the coefficients are indicating the number of molecules that are present. So for instance, in this top one here, we have one O2, so that means that there is 2 oxygen atoms bound together. Over here, we have 2 H2s, so that means there are 2 hydrogens bound together, and then we have 2 of those molecules. So we have 2 sets of hydrogens bound together. And so we don't want to mix up the subscripts and the coefficients. The next thing to think about is that when we are coming up with our chemical equations, you always want to balance the chemical equation. And this may mean having to use naming rules to write the formulas of compounds in the equation. So for instance, if we have some kind of ionic compound, say something like copper 2 chloride, then you would have to know that it would be CuCl2. So that there would be 2 chlorines in that compound. And you can balance the equations using the coefficients. So once you know what the compound is, so something like CuCl2, you would not be able to just write it as CuCl3 and change the subscript in order to try to balance it. You would have to try and balance it by changing the coefficients in our chemical formulas. So when we have our chemical reactions here, recall that the number in front, the coefficient, applies to everything in the molecule. So with this H2 here, this 2 applies to both of them, so that means there are 4 hydrogen atoms. Where in the products over here we have 2 H2Os, so that means we have 4 hydrogens and 2 oxygens in the products. So that 2 applies to everything in the molecule. Whereas with the subscripts, this applies only to the atom preceding it. So for instance, in the water over here, we have H2O, so that means we have 2 hydrogens in a water molecule and 1 oxygen in a water molecule. So that 2 there only applies to the H that precedes it. And so recall that the subscripts indicate the atoms bound together, and the coefficients indicate the number of molecules that are actually present. So when we're trying to balance something like this, we see that in the reactants there are 2 oxygens, and in the products there are 2 oxygens, meaning that those ones are balanced. We also see that there are 4 hydrogens in the reactants and 4 hydrogens in the products. So those ones are balanced. That means that the entire chemical equation is balanced. Down here we see that there is 1 magnesium in the reactants, 1 in the products, 2 fluorines in the reactants, 2 in the products, 2 bromines in the reactants, 2 in the products, and so that means that the entire reaction is balanced. We know that we have a balanced chemical equation when the number of atoms in the reactants is the same as the number of each type of atom in the products. So when we want to identify a balanced chemical equation, the chemical reactions obey the law of conservation of mass, or matter. And so we want to check that the types of atoms on both sides of the equation are the same, so that no elements that are not in the reactants are shown in the products, or vice versa. So you don't want elements appearing and disappearing. And we want to check that the number of each type of atom on both sides of the equation is the same. So if we have something like this, we have this reaction occurring where we're taking 2 of these small circles plus 1 of these big circles and combining them. So we see we have 8 of these small ones in the reactants and 8 in the products, and we have 4 of the big ones in the reactants and 4 in the products. So they should always be the same on both sides of our chemical reaction here. So I would encourage you to look at these equations on the bottom and try to determine whether they are balanced or not. So if we want to look at this, we want to determine whether these are balanced or not, and then determine why. This first one is not balanced. We see that it has 1 nitrogen in the reactants, 2 in the products, 3 oxygens in the reactants, 4 in the products, 2 hydrogens in the reactants, 1 in the products. So this would break the conservation of matter. For the second one, we see that the sodium disappears and the potassium appears. So we have a sodium in the reactants but none in the products, and a potassium in the products but none in the reactants. So again, this would break the conservation of matter. And this third one here, this one would actually be balanced. We see that there are 5 chlorines in the reactants, 5 in the products, 1 phosphorus in the reactants, 1 in the products. So when balancing chemical equations, we know that we always have to balance it. Our chemical equations always need to be balanced. So you balance a chemical equation by double checking that the formula of each compound has been written correctly. So for instance, if we have something like copper 2 chloride, you would not want to write it as CuCl3 or just CuCl. So we want to make sure that our chemical formulas are actually correct. Then we want to place coefficients in front of the compounds. So the coefficients, remember, these multiply all of the atoms in the compound. So if we put a 2 in front of H2O, that means that we have 4 hydrogens and 2 oxygens, because that coefficient multiplies everything in the compound. Then we want to work back and forth between the reactants and products until the number of each type of atom is the same on both sides of the equation. And this can be kind of a trial and error thing. So when you're doing this, you don't want to be afraid to make some mistakes. You don't want to be afraid to erase and rewrite things. So you might write down a coefficient in front of something and then just see how that actually affects everything else in the chemical equation. And then if maybe that didn't actually work out, you erase that, try something different. So again, there is a bit of trial and error in this. When you do enough practice, it starts becoming easier, but there is a bit of trial and error that you have to do for this. And in the next video, I'm actually going to go through several examples of balancing equations so that maybe you can pick up on a few strategies for it. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.